So each of the panelists is going to talk about the objectives of the program, what happened, and sort of try and answer the question, so what? So you did this great and wonderful thing, what happened? And that's often the case with DARPA programs, of course, is sometimes hard to know where that technology went or the systems went. So we're going to talk about that at length as part of their presentations. To provide a little bit of context, with any luck, did that, Jim Allburn, Mr. Francis, Mr. Leahy, Dr. Leahy. So a little bit of context, sort of how did we get here and where have we been? So literally starting back in the 60s, DARPA answered an urgent need that was coming out of Vietnam for a ISR platform that was quiet. They were tired of flying helicopters and small manned aircraft over the jungles and getting shot at by a ground fire, and they actually put together a powered glider. The 70s, most of you, if not all of you, recognize Have Blue. And then in the 80s, started DARPA's work in unmanned systems and autonomy. Again, in some cases, looking at urgent needs, in other cases, just trying to continue to push the leading edge. As we get to the 90s, a continued, again, interest in supporting the warfighter along with other manned aircraft. A. Stovall is probably the one outlier in the group. That was a ground demonstrator, actually, but is significantly important. We'll talk a little bit more about that in a moment. And then in the 2000s, a continuation and actually a re-emphasis on unmanned systems. And you see that's sort of a theme across the 80s, 90s, and 2000s, really trying to push industry and the department into the advantages and the force multiplier effects of unmanned vehicles. So Have Blue, of course, led directly to a rapid acquisition of the 117. Tacit Blue, which really took the parameters of the stealth technology that was done in Have Blue to curvilinear surfaces and the use of a radar on an LO airplane, a lot of attributes that fed into the B-2 program. Amber, after a long and circuitous path, led to Predator. And then X-31 and X-29, impact on F-22. The two presenters will talk at length about that, so I'll just let that go. And then A. Stovall really was a fundamental technology, that shaft-driven direct drive lift fan that really was an enabler for the Stovall variant of F-35. All of these programs achieved any number of other technical goals, and those technologies feed into any number of other programs. This is just meant to be illustrative of some of the things that came out of them. It truly is good fun every day being around X-Planes at DARPA. I'm not going to take up any more of anybody's time listening to me introduce all this, so I'm going to turn this over to Jim Allburn to talk about the X-29 program. Jim?
Harry, thank you so much for that warm and heartfelt introduction. I appreciate it.
20 years I've known him.
You never know that, huh? I was the program manager on the X-29 for 1980 to 1986. I was very fortunate, tremendous experience. And there we go. There we go. It's interesting in terms of, that was my main program, but I was also, I was a program manager on every one of the aircraft except Tacit Blue that was listed there in the 1980s. For short periods of time, but nevertheless, somebody had to fill in, and I certainly was doing that. I had a good time. Let me give you a couple of milestones of the X-29 program. It was first X-plane, X-airplane in over a decade, and it was actually started in 1976. Norris Krohn, Colonel Krohn, my predecessor, started the program in order to look at the possibility of using composites in order to control and manage the structural divergence of a forward-swept wing. I arrived in July of 80, and you see proposals arrived in August. And Norris sat me down and said, you better figure out how we're going to select an airplane to build, because we're going to do one of these. Not many people believe that. Grumman, Rockwell, and General Dynamics delivered proposals. Grumman was selected, and we had a firm fixed price contract in 1981, November of 81. First flight was 3 years later, in December of 84. And after 8 years of testing from 84 to 92, 422 flights, 2 airplanes. Number 1 did the envelope expansion, 2 did the high angle attack and vortex flow control. And we actually provided information and provided design options, which was the objective of the program, design options for future aircraft designs. The program was intended to be a technology demonstrator from the very beginning. The big thing I want to talk about here is, or mention, and I'll say more about it if I don't blind someone here, the transition results by the Future Applications Committee, an interesting approach that we used in order to get information out to government and industry of potential users. Say more about the, there we go. You can see the technologies on the aircraft. It's a beautiful airplane, I think. I still think it's beautiful after 34 years. The forward swept wing is the most obvious characteristic of the vehicle, and it was intended to look at the transonic drag of the aircraft. The forward swept wing would reduce the transonic drag. The skins of the aeroelastic tailored composite wing solve the divergence problem. The closely coupled canard here, in terms of, you can see that, and the thin supercritical wing. We had discrete variable camber, a three-surface control is longitudinal in terms of the canard, the strake flap back here, and also the flaperons. And it was controlled by a digital flight control system, triplex, with an analog backup. And the aircraft, the configuration in terms of with the canard and the forward swept wing was 35% negatively statically unstable. No, I'm trying. There we go. A couple comments about the environment that the program was being built in. We had no requirements. DARPA went out with a letter of intent to build an airplane and asked for from industry the ideas, the type of concepts and technologies that they felt were appropriate for future designs, and to test them out, research them. The aeronautical research was being questioned at the time with a national study that actually eventually supported the continued research and development of aeronautical technologies. Timing was interesting in terms of trying to influence the ATF competition. The contractors were obviously very interested in trying to provide a capability that the government would be interested in. The services were somewhat reluctant. Reluctance is probably a euphemism about X-planes. Stealth technology was being developed at the time, so the question about why we're doing this aircraft, and it was in the open totally. Everything was provided. We did second aircraft for risk reduction. Flight tests were originally proposed at Grumman, but they were eventually moved to NASA Dryden. And then we had a fixed price contract for a research aircraft, was interesting, but it restricted and reduced the amount of changes that were possible in terms of people wanted to make changes to it. The contractor, Grumman, actually put more money into the program, as did DARPA, after the initial phase. We initially bought only the parts for the second aircraft, and we then added more money to build it, and also the flight test program. Summary results. I think we did in fact achieve we provided technologies, proven options for future designs. The military utility was demonstrated during advanced combat maneuvering with a dissimilar aircraft. The drag reduction, which was thought to be a very critical, important piece of the whole program, was very difficult to determine, given the integration of all the technologies on the aircraft. It turned out that the canard, three-surface control, it provided excellent handling for the very unstable aircraft. This was a surprise. It was more stable, more controllable than thought. And the close-coupled canard validated and provided excellent handling quality. Structural divergence was, in fact, shown that could be controlled with the forward-swept wing. High angle of attack was flown to 45 degrees angle of attack, and it was better than the sim. And then the aircraft was actually controlled to 67 degrees during the high angle of attack maneuvering. Oh, there we go. Got to turn it. I'd like to look at the bottom section, the bottom of this chart first in terms of transition. We formed we called a Future Applications Committee. It was composed of senior government and industry technical people, VPs of engineering for various companies. I think there were 10 or 12 aircraft companies at the time. All were invited to participate, and they all did. We also had senior people from the government in terms of the NAVAIR, Air Force, ASD, NASA as well. And this group was given regular updates in terms of the good things that are happening in the program, the difficulties the program was having. And then we met at Dryden, we met at Grumman. Grumman was contractually required in order to provide that information. They did a great job of that in that respect. But it was the first time we had done something like this, and the idea was to get the information out just as quickly as possible. The group actually participated in the source selection, evaluating the proposals, the 3 proposals, evaluating and assessing the value of the technologies that were being proposed and then the likelihood of being successful. And so we took that and we made the decision in terms of selecting Grumman. Also, you can imagine that after 8 years of flying and analysis or data collection and analysis, NASA was very interested in trying to close the design loop and the audit trail and update all their codes, their design codes. And they provided that after all that analysis, they provided all that information as well to industry and the government potential clients. System integration was important, but more importantly was the high angle of attack in terms of useful demonstration, useful technology. Not so much a secret, but a reason of success. This was an IPT, integrated product team, before that phrase was even coined, in terms of the integration, the support that the contractor provided to the program, both Grumman and NASA. NASA sent people to Grumman for the last year of building the aircraft and testing the aircraft so that they were very prepared to test it and work with it when it got to Dryden. And Grumman actually had people there, obviously, during the test program. Did that already? There we go. This is just a list of the team itself, which was the IPT, Grumman, Air Force, NASA, and NAVAIR. The Flight Dynamics Lab did a great job, but they were the program manager, or the program office rather, here during the early phase of the program, first 2 phases in 76 to 80. Flight Test Center, Engineering and Test Support, and test pilots. NASA headquarters. This initially started a rather interesting connection and combination and partnership between NASA and DARPA for a number of aircraft. This one as well as a couple other ones. And of course we use the wind tunnels at Langley and Ames and NAVAIR in terms of supporting the program as well. Yeah, we didn't build an aircraft, a forward-slope wing aircraft, but if we had, this might be what it looked like. This is one aircraft, the Berkut, it's Su-47. They built one, they tested it for a while, and then it ran into budget problems in terms of continuing or stopping the testing. I think in terms of a DARPA X-Plane approach, I think it was validated, a Skunk Works type approach. That's what we had with this integrated product team, certainly. And the combination of a small integrated team, program manager, top cover from both the government and the industry in order to protect the program. Adequate funding, that was always a difficulty and always a problem. And then dedicated and talented flight test team. This bottom, an opportunity to gain hands-on experience from design through flight test, which was identified in that aerodynamics National Aerospace study that I mentioned in the beginning. That was one of the points that came out of the study. Building aircraft, having the experience, keeping the design teams together was very important in terms of, as you go forward in terms of maintaining the capability in the country. The number 1 aircraft is in the museum at Dayton. Number 2 aircraft with a spin chute was sitting out on a pole at Dryden, or now Armstrong Test Center. So I don't think either one of them are going to fly ever again, but after 34 years, it's still fun to talk about it. So thank you much.
Thanks, Jim. Thanks very much. I think with that, we'll have Dr. Mike Francis talk about X-31.
I'm going to stay in my seat for this because I have a better view of the presentation here. X-31 came along just as the X-29 was winding down, and it had its roots in the Cold War. It was not driven by technology, it was driven by a real Cold War problem, and that problem was, what happens if the Soviets come across into the West with an overwhelming force? How do we beat them back? That concern, of course, was reflected throughout the U.S. and its allies, but really prominent in those countries that were on the border, the West Germans in particular. A prominent engineer, an aerospace engineer in Germany, Wolfgang Herbst, at Messerschmitt Bölkow-Blohm in the early 70s began looking at the problem and how you deal with it. And the Germans did a variety of studies, some and eventually wound up with simulations, both computer-based as well as man-in-the-dome kinds of simulations, to prove that if you had an aircraft that could point independent of the flight path, was highly agile, it could wind up with an exchange ratio to make the result more palatable than the one we would have with equal capabilities on both sides. And that formed the root of the X-31 program. The Germans, that company then got together with North American Aircraft, part of Rockwell International. They teamed up to present a proposal to DARPA in 1983 to go create an X-plane. The result of all that was the first, and to my knowledge, still only international X-plane. We had not just the two major countries participating, but 9 agencies and numerous companies, both prime and subcontractor, both in the United States and across Europe, across Western Europe at the time. So it was an interesting management challenge to do all this. The program set itself up with 4 major objectives. The first one is to prove that an aircraft could be built that possessed the agility required, or based on those simulations and those studies, that could meet the requirements to go deal with that numerically superior force. The second major objective was to go prove it, to go assess the tactical value in a real combat kind of situation. This is with an X-plane. Those became the driving forces, 2 of the 4 requirements that never changed throughout the program, and all of which ultimately were met. We built 2 aircraft, both of them largely based in the United States, although the Germans had several key roles on the program. They built the all-composite wings, the first time that had been done, to my knowledge, in Germany, made it in the U.S. when the wings were brought over. This was in the late 80s. They also had the task of creating an integrated flight control system that blended the aerodynamic surfaces with the thrust vectoring system. And they also had the task of designing and building the all-carbon composite thrust vectoring vanes that allowed the aircraft to have the kind of maneuverability that it ultimately would attain. That agility that aircraft possessed was termed, and you'll find that in the literature, it's called super-maneuverability at the time. The program, another unique facet of the program is it took a long time to unfold. Now, there were reasons for that. The early part of the program, because it was international in nature, it took a long time to get agreements in place with all the other agencies you have to deal with when you do this kind of effort. And that itself took on the order, I want to say, about 4 or 5 years. The aircraft took about 3 to 4 years to build from the time that design began, and airplanes were produced and started flying. And then we went through 2 separate flight test programs. The first one was called the Enhanced Fighter Maneuverability Program. This is the one that was DARPA-led, the one I'll spend most of my time on in the remainder of my remarks. 6 years after that program ended in 1995, the Navy took the remaining airplane, and I'll explain what that means in a moment, and created the Vector program, which went on for about 5 years looking at certain aspects of the technology that they were interested in. Well, that was unfolding, of course, so 20 years is a long time. Lots is happening in the external environment. The major event that created issues for us was the fall of the Berlin Wall and ultimately the end of the Cold War, which occurred right at the beginning of the flight test program. And when I say it created problems, the big one being the lack of finances for DoD organizations and the Defense Department in general, given the winding down that took place after the first Iraq War under Clinton. So finding money was difficult. It forced us to be very innovative and very frugal in the way we conducted the flight test effort. The second major set of events that took place was the change in air combat itself. While the requirements for this program had their roots in Vietnam and all those 1960s, 1970s engagements that we fought within visual range, that was, by the way, a requirement to engage an adversary during the Vietnam Wars. You had to see them. The tendency with the advent of stealth and low observability was to take the fight beyond visual range, use long-range missiles and your stealth to keep you from being seen, and the whole nature of air combat was set to change. So we went from one very different set of circumstances where the technologies that we were offering in the X-31 program were in vogue to one where everybody said, well, we don't want to go there again, even though most pilots assumed that if you got within a many-on-many combat exchange, you would ultimately wind up within visual range and have to be able to do some of this sort of maneuvering. We, in the flight test program, one of the first things we did because of that funding shortage was find a way to accelerate the envelope expansion. Given this airplane's abilities to fly up to 70 degrees angle of attack routinely, it was pushed to 90 on a number of occasions. To point independently of its flight path, you can imagine the number of parameters you'd have to measure to do a standard flight test envelope expansion. My calculations at the time said it would take on the order of anywhere from 4 to 12 years, depending on what assumptions you made. I had 2 years worth of money left at that point. So we convened a meeting in Antelope Valley at one of the hotels for 3 days, sat down and tried to figure out a way to do this in a much more rapid way, and came up with this concept of maneuver milestones. The group defined 4, and I'll show them to you shortly in a video, that sort of captured the personality of the maneuverability of this aircraft. Following that, and by the way, we did that, we'd planned to do that in 18 months, we wound up actually executing it in 6. So the team proved up to the task in terms of accelerating the envelope expansion portion of the effort. We then went into close-in combat, first with the F-18s that NASA had as chase planes. We thought this would make an adequate adversary. We created, using wingtip tanks, inertial matching to the X-31, the difference being the F-18s didn't have the thrust vectoring. And we flew a number of engagements, close to 80 as a matter of fact, with those airplanes. The problem, of course, we had was the results came out way too positive. We didn't believe what we were seeing. We thought maybe it was test pilots flying in those airplanes that were part of the issue. So we started engaging active combat squadrons, F-14s, F-15s, F-16s, F-18s from the fleet. And the results, when we went up against aircraft that were similarly equipped, had similar performance parameters, thrust to weight, other things, the results came out the same. So we were very successful in demonstrating the effectiveness of using post-stall maneuvering in a kind of engagement where you're up against a numerically superior adversary. Because of the other changes that occurred during that period of time, we thought we had to prove to our customer base, the services, that the same technologies that we were using for this cosmic maneuverability had application elsewhere. So we did a number of demonstrations to prove that the same technology could allow you to fly at supersonic speeds without a tail. The thrust vectoring simply did what Newton said you have to do with forces, providing the restoring forces and moments, and we were able to showcase that on the other end of the envelope. We also introduced the first helmet-mounted displays to within visual range combat aircraft, and we also developed a concept called ESTOL, extremely short takeoff or landing, dramatically reducing runway lengths on launch and recovery that the Navy was interested in, and in fact formed the basis for starting that second program called Vector out there in the 1998 timeframe. I mentioned that they used one aircraft. It turns out the last thing we did in the EFM program, we had planned, and we did go to the 1995 Paris Air Show. We're the first, and to my knowledge, only X-Plane to perform in front of the public. We did it there. But 4 months prior to that, one of our 2 airplanes augured in the desert, the first major accident they had at Edwards Air Force Base. And I mention this because only DARPA, with their perspective on risk, would allow a program manager to take the remaining X-plane and go after the Paris opportunity. Gary Denman, then director of DARPA, gets the credit for that decision, and we were able to fly every day but one at Paris that year. So let me give you a quick quick snapshot with a short video. In fact, let's start it. I'll try to narrate as we go. So the first thing you're going to see are the 4 maneuver milestones. The first, sustained flight at 70 degrees angle of attack. These are all aerodynamic and aeronautical firsts for an X-plane. This is a velocity vector roll while the airplane's at 70 degrees angle of attack. We did them in 360-degree rolls in both directions, eventually at very high rate. This is the first time we did a rapid pitch-up successfully into the post-stall condition. And you take those maneuvers and put them together. We did this maneuver called the Herbst maneuver. It's the airplane equivalent of a swimmer doing a flip turn in a swimming pool. It's a high-speed entry one way, a 180-degree turn the other way using the high angle of attack to precess around the velocity, the flight path, and then heading out the other way in the opposite direction. This is the pilot simply showing you how he can point that airplane no matter which direction it happens to be heading. We did a number of these things before we engaged in this kind of air combat. This is one of the vignettes, it's a short one, where the F-18 and the X-31 are shown with animation based on real flight test data. And up in the upper right, you're looking out through the HUD camera on the X-31. You can see the F-18 come into sight and how the virtual gun is tracked on him for a short period of time to get the kill. And this is the kind of engagement we ran with neutral starts, head-on starts, and also negative starts. This is the Paris routine. The 4 maneuvers we did every day in Paris, as I said, but the first one is a takeoff to a vertical climb followed by what's called a post-stall loop, which you'll see shortly. Coming right here, instead of going over the top the normal way, he pulls it through post-stall to 70 degrees angle of attack and then begins a heading reversal. And of course, when public saw this happen at the air show, it was like an E.F. Hutton moment. This is the aircraft doing we call it the Mongoose maneuver, our answer to the Cobra. It's a skidding turn with the airplane winding up at 70 degrees angle of attack. Sustained flight, 40 knots, going away from the crowd so the airplane looked like it's just hanging in the air. We wanted to do a square dance around the runway with this technology. They wouldn't let us come back toward the crowd, so we decided to do 2 90-degree turns. This is the first time it was attempted. The guy who's flying the airplane right now is Chief Test Pilot Fred Knox. I say Chief Test Pilot, he was for Boeing before he retired. And the first time he did it, he didn't get 2 90-degree turns, he got a 180, but it's nonetheless the first time it was attempted. And then the last maneuver is a high-speed entry, almost sonic speed, heading up to 5,000 feet, showing you the airplane's pretty quick as well. And then another post-stall loop followed by a double heading reversal, assuring you that this is nothing about inertia. This airplane is fully controllable in virtually every stage you can put it in. You'll come away right here. So since my time is up.
Well done.
Not bad.
It's going the wrong way. There we go. Dr. Leahy.
So about 20 years ago, some of the men on this platform had done what they did, and they also had gone in and DARPA done the Tier 2, done the Tier 3, kind of done the ISR, been looking for different ways to take on the next step, and everybody said, well, the next step ought to be we should do a combat vehicle. And so a variety of name changes but came around to being what was the X-45 Alpha at the time, or the UCAV program, morphed into a lot of other things went along the ways. But I always started every briefing for the whole time I was on the program with that chart. And the point is, it didn't change, right? You just put the time up front, you figured out what it is you wanted to do. The revolution you wanted from a breakthrough capability was twofold. It was that I want to be able to do something, in this case, seed strike missions, which are arguably some of the most demanding that you have to do, and a clear need to be able to do them, and not one that people would prefer to do if they didn't have to. And then also at an affordability price point, which jokingly at the time was 1/2 of the JSF from an acquisition standpoint, which now I'd get a lot more money I'd been able to do that with. And then about 75% reduction in the cost of operation, because the thought was, hey, I can just keep these in containers. I don't need to take them out. I don't need to fly them for proficiency. So you spent a lot of time getting that right, and then you stayed with it, right? You didn't wander. You weren't chasing squirrels. You were after that one kind of thing. The other thing from the beginning that was different than the other two programs we've talked about here is this wasn't an airplane program. This was a system program. This is about how can I get a capability where a series of technologies that kind of coalesce are all in the tier 5, 6 kind of range and put them together. So we started from the beginning of looking at what an operational system had to be. You think back, and I've had the times I've done in the lab and others, this wasn't how you did things. You had your stovepipe, and you had your aero guys, and you had your other guys, and you had your software guys, and they didn't talk to each other unless they had to come together for a proposal. And so this was spent the time and really created a day in the life and looked at all aspects of this. We had people from Eglin load weapons on this, and we dropped them. We transported it in its container inside a C5. Right? All those different elements were involved as you went through here along 3 major segments: the mission control, the airplane or the air system itself, and then the container that it was going to be stored in order to support mission part of it. And that was the key. You had a concept that then became kind of standard but hadn't been done before at DARPA, which was you took an operational system and you used that to decide what your demonstrator would be. There wasn't a set of requirements that went out with this other than kill seed targets and come home. And that, to do that right, you needed also to change the game, and you needed to have access to all the right things to get an operational design that people would stand behind. Right? So we were an acknowledged black program, right? An oxymoron to some people, but they work. And we used up front that knowledge, and we had the keys to the kingdom, and we worked with ACC, we worked with now is the Life Cycle Management Center, AFMC, others, the flight test community. And we came up with, this is what the mission's got to be. This is a realistic design. We ran it in suppressor with the Air Force's experts on that. Did it all up and said, okay, here's what comes out of that. Once you have that, then what do you need to get from here to there? And we coined the term technologies, processes, and system attributes, meaning that it wasn't all about the technology. There might be processes you needed to be able to do. There's attributes of the system. And that then translated into the demonstrator system that you see there. And it was focused on flight validating those things that needed to be flight validated. And it also had, like I said, we built the containers and we shipped them and other things with it. It was always meant to be a spiral development program. Today we wouldn't use spiral, it's a bad word, we'd use agile. But the idea was you don't know what you don't know. And you don't, right? And so you wanted to start out and say, well, we're gonna go build an airplane and we're gonna do it quick and we're gonna build the other parts of the system, and we know by definition it's not gonna be exactly right. Right? If that airplane had its wing about 15 inches too far back, its control surfaces were about 25% too small, that mission control system, you learned very early, actually, in the Pentagon, your head goes better this way than this way. So we had to change that off, and the containers were different. But you learned a hell of a lot that you wouldn't have learned any other way. All right, I'll always remember the first time we took the mock-up down to Eglin, and we said done all kinds of 3D animation and everything on it. We had 2 pages of stuff before the first 5 minutes went on how we screwed that all up. Right? Because you had to build it, you have to get it out there, you have to have people to be able to use it. We always intended for there to be a B program, where we kind of stretched it, so we did the F-18 thing to it. And then follow-on blocks were going to come along as you went through. But what that also allowed you to do was to learn a little, test a little, fail a little. Right? You can keep your failures small, so you can hide them. You can... because every time, that's the thing on an X-Plane program, right? Every time you fly, you bet the program. Every single time that you go. But you could get incremental progress, and you could then be able to secure what you needed to do financially, funding-wise. We had $1 billion budget on this before it flew. All right, we started with $180 million. We had it in the budget lines $1 billion before we flew. So you knew how to be able to work that process and get that to be able to come across and to get there. But I'll also tell you that until software takes the cover of AvWeek, which is my one dying request, that this was about the plane, and we knew that. We built the plane with the last bit of dollars we had. Then we went and got more money because, of course, now you got a plane. You can't stop now. This is a trip down memory lane of kind of what we thought at the time in our naivete of what we could do and could have done. But I'll argue in terms of the sense of an impact, when this started, The Predator didn't have weapons on it. You know, the Predator had weapons on it and got to go that quickly because we had already been in negotiations with the State Department on how the ITAR stuff didn't really, or the Intermediate Ballistic Missile Treaty didn't really hold. This led into what was the JUCAS program. It led into the Navy kind of programs that have been going on and others along with that. And you can argue that it now kind of came back around first circle last Friday when Boeing, who had been the prime on this, got back to win the MQ-25 program. Oddly named the Stingray, which is a bit of revenge because that was the name from an Air Force joint program with DARPA. That was our test flight name out at the test center. So the Navy named something after an Air Force program for us. But that's a long, strange path that you go on. You never know when you start to snowball down the hill where it's really going to end up. But if you stay with it long enough, it will. And so that's kind of the predecessor of where that came from. But these are the kind of things, you know, if you want to be able to go fast and go faster, you got to be able to do, but it's still structurally very hard once you need real money. Then I'll just end with this. This is the picture I always ended with too. Both of those are in the museum. That was one of our goals. We wanted to be the first kind of UAV program that started out with the same amount of airplanes as it ended with. No offense to some other people in the audience.
Hey.
I'll take that standing on shoulders of giants thing, you know, and kind of moving a step forward for them. And, you know, and a couple other, and then mock-up is actually, that was just the plywood one. Things changed right after that. As Mike said, other things change as programs go forward, and you always got to go with those for them. And, you know, the other final thing I'll leave you with is that, you know, there's no better program than you can be on than an X-Plane program as a DARPA Program Manager. Right? There ain't no better, right? I've done them. You learn a hell of a lot of things that you didn't learn. You get tested in a lot of different ways. And when you come there, be prepared to make those choices, right? People who say it doesn't matter, passionate leadership matters, right? Risking your career matters, all right? And those things look back and you look like, oh, that was all great and fun and easy. No, it wasn't, right? And everybody who's been involved with those, you know, is a bet big, think big, bet big, sometimes win big, sometimes fail big. But you're always going to move the stick forward and move where you're going to go and how to do it. I encourage anybody who's ever got that opportunity to take it and go do it. The repercussions of that will spawn a lot of different things for you, both from the program and for yourself and your career. But there's no greater opportunity to do that and to be able to kind of follow your dreams a little bit and try to make things different and happen. But again, where they'll end up, nobody ever knows when it starts. Thank you.
Thanks, Mike. And I did get the second one back in the air.
Yeah.
So we do have time for some questions. Hopefully everybody's figured out this DARPA D60 app and has been sending them in. Mr. Auerbach has the first one. I only have 3 seats at the table that could talk. I ran out of time. There's no reason to go there. But as I said, I did get the second one back in the air 9 months later. The first question, actually, I'll take this one. So the question is, why hasn't DARPA had any X-Planes in the last 10 years? The point of the matter is that some programs get to flight test and some don't. So there's been a number of projects over the years that have started along a path. Don Woodburn in the audience, we had UCAR that got through PDR. That ended for a variety of reasons. VTOL X-Plane, a recent program, we did build a subscale demonstrator and learned a lot, and the decision was made not to go forward to a full-scale demo. So that's just the nature of the beast within the agency. There's still a lot of activity, as those of you who follow what's going on in TTO these days with airplanes. Just the fickle finger of fate, so to speak, as to what actually gets to flight test some days. So that one. This one we'll turn over to the panel. So I actually would like each of you to take a shot at this. We'll start with you, Jim. So the question is, what do you see as the next aviation frontier requiring an X-plane demonstration? If you want to take a shot at it and just pass it along.
I'm somewhat at a disadvantage here in terms of being out of the business here for some time. But I've always, and I will continue to support single-staged orbit, horizontal takeoff and landing. The old X-30 NASP program, that was involved in that to begin with, and I think that's still an area that ought to be looked at. Whether that's the next one, I doubt it. It's further out, but that's what I would say.
Okay, Mike?
Yeah, with respect to X-Planes, from a technology perspective, NASA has a number of X-Planes in the queue right now, including a supersonic demonstrator that's about to kick off with Lockheed, I think, as the contractor. But for DARPA to do an X-Plane, there has to be a military perspective. And I'm going to be a little bit controversial right now. Because if I'm at DARPA, knowing what I know, I had my hands in JUCAS and the program before UCAV as well as X-31. My next X-Plane would be an unmanned demonstrator that could take out a manned fighter. The technology to build the airplane that is both more agile than I showed you there, as well as stealthier than a manned aircraft, because we've already done that. Can't go into the details there. Along with the intelligence to do more than the physics-based activities, which is where we have been with most of this, what we call autonomy today. If you look at all of that, we do the flight control, we do everything up to the point of mission management, but now the computer starts to have issues. That's where AI enters the picture and we're more on the edge. Inasmuch as DARPA likes to push the envelope and, again, prevent technological surprise or create it, it's not inconceivable to me to create the right airframe with the right software and the right machine intelligence to build that machine. The hard part's going to be on the machine intelligence side, in my view, not on the mechanization of the aircraft itself. We even back when we were building this air-to-ground machine called UCAV, we're thinking about the air-to-air version of it that might pull 30 plus Gs and turn the chess game of air combat within visual range into a calculation. So that's a 30-year-old thought, or almost that now. So I do believe, having worked with AI folks for the last decade, that we're on the precipice of being able to do something like that. I don't know if it would get to a flight test point at this juncture, but it's something that a place like DARPA ought to be looking at if you really, really want to be honest with yourself about the state of the art in this technology.
Thank you. Mike?
I'd probably dovetail a little bit on to what Mike said in the sense of not so much, back if I look at the next kind of generation of system, the thing we wanted to do and we're never able to do and still haven't done, is really take those systems out and, get them to their potential, right? There's a lot of good reasons why a tanker might be useful for the Navy, but that doesn't scratch the potential of what we even demonstrated, 12 years ago in this, and there's been leaps of changes. And what I'd like to see them go after is, build up, and it's got to be representative size, right? Simulation doesn't matter, subscale doesn't matter. What matters is being able to go out at a red flag and be able to participate as you normally would and be able to kick ass, right? That's what's going to move the needle. And to do that, you got to make enough investment for that to happen. So I want to see them wolf packs, right? I'm not a swarm person, but wolf packs, a couple alphas, go out there and engage into that environment, be willing to make that kind of investment. And maybe you could argue that we weren't ready to do that before, but certainly those technologies have moved along enough to be able to do that with, and we can dovetail that along the way, create a couple of those systems that also had some other unique attributes to them to be able to use as well. Because I don't think it's going to change that way on our own unless somebody else does it to us, and God forbid, that's the first way we have to learn that lesson.
I don't think there's any doubt that, the X-Planes have pushed the services, right? DARPA X-Planes have pushed the services into areas that they wouldn't have gotten to nearly as fast. And especially in the UAV world. I mean, the services were drug kicking and screaming into that,
Well,
into
same
that
is true
world.
with stealth, by the way. But.
Right, yeah, the Have Blue story of dragging a general into the control room and having it fly right over, and the guy in the missile battery never picked it up. Right? I mean, it really was a prove it works, and prove to the services beyond a doubt that it works. Mr. Arbach, next up. Two at a time, terrific. I'm not touching that one.
Time's up.
You might not be able to.
Oh, you want to take this? Okay, sure. So any of you can take this one. Anybody who'd like it. It's what are your thoughts on the canard rotor wing concept applied to the X-50?
No thoughts.
I don't know.
Those of you familiar with canard rotor wing, it was actually on one of the early slides. Canard rotor wing had all kinds of issues at the time.
Yep.
Most of those had to do with controls, had really very little to do with the airplane itself. It was a controls problem. How it applies to X-50, I guess I'm a little bit uncertain how that would work. I don't know, whoever asked that question, I'd be glad to talk to you after this is over and maybe try and understand a little bit better where you're headed there, but I don't know what else I could say about that that would be germane. So Mike, you introduced this, Mike Francis introduced this thought, so I'll let you take it. It says, why didn't tailless technology become common in fighters? X-31 demonstrated what you could do by emulating the tail being missing. What stopped that from moving forward to date?
Well, first of all, it is moving forward, but only conceptually. If you look at the Air Force's next generation set of designs, at least the ones that the services are advertising, you see lots of artist conceptions of aircraft without tails. So it's not impossible. It's interesting that all the UCAVs that were in that program, none of them had tails. They didn't always use thrust vectoring to achieve that, but they were all tailless aircraft, subsonic in this case. So it's out there. I mean, I once asked a fighter pilot that question. He said, I got to have a place to put the tail number. And I think he was being facetious, either that or had too much to drink at the time. But the point being is it's a technology that's there right now. Thrust vectoring, as I discovered on that program, and in the JUCAS effort with the Boeing X-45 airplanes. I had a chance to work with the X-45As and the C as well. Very powerful way to generate forces and moments. Much more control authority than you get with the aerodynamic surfaces, and of course much less observability. Why it's not standard, I don't know. It's an issue with high bypass engines that you find on commercial aircraft, and I understand there's a need to reinvent that technology for that application. But for the modern fighter class aircraft that demands high thrust at certain points in its envelope, I don't know why thrust vectoring isn't standard. Mechanical nozzles, by the way, were part of the problem back then. There were several companies that built them. They were very Rube Goldberg-ish, I guess is the best way to say it, lots of moving parts. But with fluidic thrust vectoring, which came along a decade later, you can take it by itself or it with some mechanical vectoring and make a much simpler apparatus physically and more efficiently, and that's what I would be chasing if I were building that airplane again.
And it should be pointed out, MQ-25, the Boeing design, is a tailless vehicle, again, subsonic. So there's all kinds of issues going to supersonic in and of itself without a tail, but it is moving along, clearly. So I think, Jim, I'm going to give this one to you, because I think your presentation did talk about this. It says, going in with little or no requirements, how did you fight against requirement creep and prioritize the design decisions you had to make?
Interesting. I think the fixed price contract had a lot to do with that. DARPA went out with a letter of intent or interest, which I guess would now be called a BAA, that was before that was used, to the three aircraft companies that actually proposed. Two of them had been participating and actually did the wind tunnel testing of a half-scale semi-span wing in the tunnel to show that you could control the divergence. But the what was the question?
The requirements creep
really. Yeah, the fact that again it was a fixed price contract, and
big motivator.
It just there was no. We bought the proposal. That's what Grumman was going to build. We had to add to the contract in order for the flight test. We had to add to the contract, money to the contract in order to build the second airplane, because all we bought initially was pieces. And it was determined that it was better to build the airplane, even though it might cost a little bit, than to have pieces lying around if something happened to number one. So it was number two was ready to go, and they were able to put a spin chute on it, and it did the high angle attack work. But it was just no way. Grumman wasn't going to add to it because it was going to cost them. And they did put a bunch of money into the program, but it was primarily in the flight control system design and fabricate or makeup. So it was easy. It was easy for me.
So Mike Leahy, so the question is, what considerations would lead you to recommend building two versus a single X-plane?
Oh, well, one, seldom that you get through a program with only one, is witnessed by a lot of different things. And it's just, the cost, we looked at that. We looked at subscale, we looked at, 1, 1.5, and At the end of the day, there really wasn't that much price difference. Plus, one of the key things we wanted to demonstrate was collaborative behavior. And to do collaborative behavior, you need multiple airplanes. And again, simulation don't cut it, so you wanted to have those airplanes to do that work with. So 2 was really kind of the compromise that came about through that. And we added them to trail and we built them up and we were able to use them to do those demonstrations. So as part of the program requirement was that, and it was what we wanted to be able to achieve. And there's not really, by the time you do the design, the actual cost of building the vehicle, especially if you didn't have to put the engine in it, it's not that much different.
Get to a system is with one system.
No.
On the X-29, there was almost no question about needing the second airplane, given the static instability of the vehicle and the likelihood that something was going to happen. It never did. But so it was easy to do, and as Mike said, it was not that more expensive to, after buying the pieces and the parts and everything else, to build the second airplane. And then when it was time to do the high angle of attack testing, we put a spin chute on number 2, and number 1 came down. So it was number 1 was providing pieces and parts to keep number 2 flying, and number 1 never flew again. But it was, it made sense, really. We couldn't afford not to build it.
And it's unrecoverable, right? If you have an
Exactly.
incident and you only have one, then you're done. Right?
And I think that was the experience, the X-29 experience was the reason X-31 did too also, about 2.
And as Mike Francis will attest, you haven't lived till you've been through a major accident investigation.
Well, I will admit it was unique. We cleared the remaining airplane for flight in 2 weeks. Now, I don't know, the NTSB can't move anywhere close to that fast. But we had the best documented accident in aviation history. 30,000 foot worth of telemeter data telling us exactly what was wrong with that airplane as it augured in. That's why we cleared the other airplane so quickly.
So with that, I'm going to try and wrap this up. I want to thank the 3 panelists, and it was really enjoyable to get back together with the 3 of you and hear about your experiences over the last 20 years. Thank you very much.